Mr. Sams, hey, I got a question for you.
What's that?
You know, we are teachers of teenagers.
We are. They're a funny lot, aren't they?
Are they? They're fun, yes. But, I've got a question for you. What happens to all high school romances?
All high school romances, they all break up.
That's kind of negative, Mr. Sams.
Well, I've seen 2 exceptions to that rule in my 10 years of teaching.
I'm not sure I've seen any. So
No, not even my 10 years of teaching in my life, come to think of it. Yeah.
Yeah. No. Yeah, I always ask I remember asking some of my old high school friends, so how's so-and-so? And, of course, the answer is,
right.
No.
Yep, I have one friend that I went to school with who ended up marrying his high school girlfriend.
Wow, yeah.
Yep,
so all high school romances break up.
They all do.
Folks,
yep.
That romance that you're in right now, it's going to break up.
Yeah.
Just, sorry.
Yes.
We're being pessimists.
Yes.
But, that actually applies to today's lesson,
It does,
Mr. Sams.
yeah.
Because we're going to talk about how something always breaks up.
Yep.
All the time.
Yes.
100%.
Yes, we call that dissociation.
Dissociation. So, actually, when you break up with your girlfriend next time?
You're dissociating.
You're dissociating.
Yes, so if we dissociate, we can just...
So, we're giving you some new language. Hey, we're dissociated.
Yes.
We'll reassociate now.
Reassociate.
Yeah, there we go. Okay, we're back. All right.
I got a new chair.
Hey, I see that. It's cool. Yeah, because you're back. Yeah, you cracked your back.
That's why I was so sour in the last one.
Yeah, the sour. Hey, the definition of a strong acid is that it...
Completely.
It's like a high school romance.
Yes.
It completely dissociates.
It does.
All of them. All the time, 100%.
Always.
Just like a high school romance.
Yep.
Sorry, girls. I know you've got this romantic notion in your head, but
yeah.
No. Okay. So we should probably show that chemically.
Okay.
So if I've got now, should we talk about what strong acids are?
Yeah, we are completely dissociating.
All right. So for example, one strong acid is HCl.
Yeah. Oh, you mean list which ones? Yeah, we'll do that in a minute.
Okay. HCl is a strong acid, and Mr. Sams actually kind of got into this a little bit a minute ago. If you start it as a gas and then you put it in water, we could put water here. It breaks apart into H positive, AQ. Plus Cl negative AQ. That means all of them. So these are like our little couples, and they're all happy, but then they don't like each other, and they break up. 100%. That means there's actually 0 of these left over. There's no couples left over. There's only single boys and single girls. Sorry, 100% of them.
Yeah, and to be perfectly honest, it's like 99.9999999.
Well, that's probably like with your one friend.
Exactly.
No
He is
friends.
the one exception in the world.
Yeah. Okay. So that's completely dissociate. Now, we should also talk about, there's a list. I don't think we have a slide on this.
Yeah.
There's a list of strong acids and a list of strong bases. We'll talk about strong acids. So how do you know if an acid is strong or weak? Well,
you learn the 6 strong ones and the rest are weak.
Yeah, so there's a list of 6 strong acids.
Right. Now, this is not exhaustive list. There are some really bizarre, weird ones out there, like fluoroantimonic acid, that we will never, ever, ever encounter in here.
One.
Oh, yeah, they're called superacids. They're like ridiculously freakishly
I didn't know the name
scary.
Of that one, I've heard of the superacids. Don't mess with those.
Yeah, we're not even going to go down that road in here. So we're going to learn 6 strong, and for the rest of our purposes, the rest are weak.
So I already mentioned one
HCl.
of them, HCl. Another one that we've played around with in class is nitric acid.
My personal favorite.
I love that acid.
H2SO4.
These are sort of the big 3. These are the ones that every chemistry department has lots of.
Yep.
The next few, they don't typically have
not
a
so
lot
much.
of.
Yeah.
But they're still strong acids.
Yep.
Perchloric acid, HClO4.
Yeah, you don't want perchlorates lying around.
No.
Those are nasty.
HBr and HI.
And then the happy acid.
Hi.
Hello.
So that's the 6 strong acids.
Yep.
Every other acid is weak.
For our purposes.
Yeah, for our purposes. There's the superacid thing.
Yep.
Now, weak acid is kind of like, hopefully, like marriages are supposed to be. Only a few of them break apart.
Right.
And so it only partially dissociates.
Right, and kind of the general rule of thumb, if the strong acid is 100% dissociation, the weaks we say about 1%. Now, that's kind of a squishy, fuzzy number, but it gives you a ballpark.
Because some are actually 1%, some are 5%, some are 0.5%. Yeah. So a typical weak acid is acetic acid. Now, while we're at that, acetic acid comes from acetate.
Right.
And if you recall acetate, CHO232 negative, right? C2H3O2 negative 1. That's acetate.
There it is.
Going to mix them with the H positive. So that is HC2H3O2. Now, watch what I do. I'm going to say AQ right here.
Because it dissolves in water.
And I'm going to draw a double arrow. I'll talk about that in a second, right? H positive, AQ. It looks just like the other reaction, except for the double arrow. The only thing you see different here is this double arrow. The double arrow indicates that the reaction is reversible. We call it an equilibrium arrow. And that means that only they kind of go back and forth.
Yeah.
And so this couple breaks up, and it makes this boy and this girl, but this boy and this girl, if you will turn around and make a couple. And usually you've got to have, like, let's say 98% if this is a 2% acid, and maybe 2% over here, something like that. And so 2% are singles, 98% are couples, if you will. So that's the partially dissociated. Again, how do I know which acids are weak?
It's the rest that are not the 6.
He's not one of the 6. So acetic acid is not one of our list of 6. So he or they, whatever you want to call them, are a weak acid. So they partially dissociate.
Right, and we're going to show you a little clip here in a minute, and we'll visually demonstrate how this works.
Yeah, I think so. Here's actually a picture of how that might work. Here is a strong acid before dissociation. Afterwards, notice there's no purple line. And then for a weak acid, we have HB, whatever, just like a letter or whatever. And then mostly is HB and a few H's and a few B's.
Yep.
Yeah. All right. What about a strong base?
It's basically the same thing.
Yeah.
Strong base, complete dissociation. Strong acid, complete dissociation. Strong electrolyte that we learned in Unit 9, complete dissociation.
So 100%?
Yeah, so it just so happens that strong acids and strong bases are also strong electrolytes.
Yeah, I just thought of something, but I'll save it. So let's give an example of a strong base dissociating. So NaOH is a strong base, and we'll talk about how you know them. And it's typically a solid, actually. And when you drop it into water, it will dissolve. It will not just dissolve, but completely dissociate into sodiums plus hydroxides. Notice that this produces hydroxides, and that's how I also know it's a base. So if you produce hydroxides, it's a base. These other ones, I don't think we said this, but if we go back to our acid one, notice how in this acetic acid I made the hydrogen ion. That's how I know it's an acid, because it makes the hydrogen ion. This one produces the hydroxide. It completely dissociates. Now, how do I know which bases are strong?
There's 2.
Yeah,
Well, we're going to deal with 2. Sodium hydroxide
There's
and
only 2 strong
hydroxides.
acids, NaOH and potassium hydroxide.
Right. Basically, the group 1 hydroxides are
So
strong.
technically, if you really want to get excited here,
Yeah.
you could also conclude rubidium, cesium, and francium hydroxide. But these guys are so rare or very expensive that no one ever uses these. They will only use these 2 right here. One thing I should say about strong acids and strong bases both is the reason that they're strong acids and strong bases is because the bonds that hold them together are weak. That sounds odd. They have a strong acid, but they're weak bonds. Well, if you think about it, since they completely dissociate, then they're held together by a weak bond. Well, think back to the high school romance. The bond that holds the boy to the girl is actually quite weak. Otherwise, it would last. Sorry, we're being pessimists. And so, therefore, they don't last. Yeah.
All right.
And then the last one is the partially dissociate, or what a weak base is that, of course, it partially dissociates. Now, these are kind of weird, though.
Yeah.
We should talk about that because most weak bases are actually not hydroxides.
No, there are a few, like your group 2 hydroxides, say magnesium hydroxide.
Well, let's do one of those first.
Calcium hydroxide.
So calcium hydroxide is a weak base, and when it dissociates, it's also typically found as a solid. Now notice that the key thing is I'm going to draw is the double arrow, Ca positive 2, aqueous plus, this will be 2 hydroxides, aqueous. So that's a weak base.
Yeah, and we call these the dissociation reactions.
Right. But the more common type of weak base are actually the nitrogens. We talked about that briefly, about the tongue in the last.
Yeah, with the nitrogen there.
So a common weak base is ammonia. Now, the thing that confuses students about this is, of course, you have to produce hydroxide to make it a base, but there's no O's in NH3.
But when to have a base, just like an acid, it needs to be dissolved in water.
So we're actually going to put the water in the reaction. Now, notice how I write water. I read it as HOH.
Ho-ho.
Yeah, ho-ho. Yeah, it's like,
Ho-ho.
I'm going to draw my double arrow, and what's going to happen is this hydrogen is going to connect with the ammonia and make something we've seen before, ammonium, and then that kicks out the hydroxide.
Right, because if you take an H off HOH, you're left with
OH. And so the most common type of weak bases are actually these nitrogen-bearing compounds where they kind of steal, not just kind of, they do, they steal a hydrogen from the water molecule and then leaves the hydroxide. So there's lots of these.
And we're going to give special names to these things here in, I think, the next lesson.
No, I think we should do it now because I don't think it's done in the next lesson. These are called, NH3. Now, this is called ammonia right here. AMMONIA. But as a group, they're called what? Amines. So amines are these weak bases that have nitrogen in it.
Yep.
In fact, the word am has to do with nitrogen, isn't it? That kind of it's like the Greek for.
Oh, I don't know. I'd have to look that one
I
up.
think that's right. So that's where it comes from, I'm pretty sure. Let's do a quick little video clip that kind of illustrates all this, and we'll finish with that.
I want to talk about the difference between a strong acid and a weak acid. So I have a molecular model that represents hydrochloric acid, HCl. And HCl is a strong acid, one of the 6 strong acids that exist, or well, there's more than that, but for our purposes. So what that means is it completely dissociates. So if I take this HCl, which typically is found as a gas, as I've symbolized here in the chemical equation, if I drop it into water, it will dissociate completely into hydrogens and chlorides. That means it's going to break apart into hydrogens and chlorides. Now if you notice over here, I've got a whole bunch of HCl's. When I say completely dissociate, that means all of them will dissociate. So I would break apart this one. So what they look like is, well, all the yellows, all the hydrogens, are broken apart from the chlorides, and they're completely dissociated. Now, this is actually not the way they look, because they would all be mixed together. They'd all be mixed together and be randomly placed in the compound. Now I want to talk about weak acids. Now weak acids, the important definition to understand with the weak acids, they are substances that partially dissociate. That means break apart into ions. So here I have an example of a weak acid from a molecular model. It's acetic acid, HC2H3O2. And so the yellow here represents the hydrogen, and the red is the acetate. It actually be more complex than this, but that's close enough. And so what it's going to do is it's going to partially dissociate. That means that only some of them, when added to water, will break apart into hydrogens and acetates. So I'm going to break apart one, and frankly, that's probably about right. What's going to happen, most of them stay together as HC2H3O2, acetic acid, and a very few break apart. Usually it's 1 in 100, maybe 5 out of 100, so it's like 1% or 5%, sometimes less than even 1%. So this is an illustration of a weak acid that partially dissociates.